The focus of this video will be on nucleophilic aromatic substitution. But to introduce the topic, I'd like to talk about substitution in more general terms. We're going to start off by looking at these two reactions at the top of the page, which are both substitution reactions, but specifically they're substitution reactions that occur at a pi-bonded carbon. So you could see this substitution reaction that's occurring is happening at the carbon-oxygen pi bond, whereas this substitution that is occurring at a carbon-carbon pi bond. We've seen this reaction before. This is from chapter 10 of our textbook, where we looked at the reactivity of carboxylic acid derivatives. See if you can figure out the reagents and conditions that we would need to affect this reaction. Hopefully you could reason that this reaction would go if we added sodium hydroxide in water. Since we're making a carboxylic acid, we'll have to acidify this at the end, and so we'll just do a workup with aqueous acid. Right, so these are the conditions that would allow this reaction to go and afford us with a carboxylic acid. If we think about what is happening, the hydroxide anion is going to add to the carbonyl carbon. Those electrons will shift up to the carbonyl oxygen, and we form a tetrahedral intermediate. Once we form this tetrahedral intermediate, it will be unstable and will undergo an elimination where the chloride anion will be kicked out. And that will lead directly to the carboxylic acid. Now, under basic conditions, right, once we form this carboxylic acid, we'll pluck off this proton, and that's why we have to do an acidic workup once the reaction is done. I'm not showing that mechanistically, but we should be able to understand that why we have to do an acidic workup for this reaction. Now, it's important to note, whenever we undergo substitution here, what is happening is that it is an overall substitution that comes from the combination of an addition step followed by an elimination step. Right, so this is going to represent substitution at the carbonyl. Let's take a look at the second reaction. So this is probably not a reaction that you've seen, but maybe not one that is super surprising. So think about the conditions that we would have to to get this reaction to go, right, to accomplish this substitution. Well, in this case, really all we need to add is methanol. If we wanted to go a little faster, we could add methoxide, but methanol is just fine. All right, so maybe at this point, pause the video and see if you can draw out a complete mechanism that accounts for this substitution. If you drew the mechanism right, hopefully you should see that the methanol will add to the beta carbon, right? So this is going to undergo conjugate addition. Even though methanol is considered a hard nucleophile, it's still adding to the beta carbon because that chloride that's attached to the beta carbon is going to activate that beta carbon, right? It's pulling electron density away, so that makes the beta carbon a little more electrophilic. So when this happens, just like in other conjugate additions, we're forming an enolate intermediate. And now, rather than protonating that enolate, because we have a beta leaving group, that enolate can reform the conjugated system and kick out the beta leaving group. And then to get to the product, it just involves plucking off a proton and forming that product. right? So this reaction would represent substitution at the beta carbon. Of an alpha-beta unsaturated carbonyl system. Right? In both of these substitutions, it's very important to note that substitution at a carbon pi system never happens through a direct mechanism or a concerted mechanism, right? Substitution of the carbon pi system always must go through an addition followed by an elimination. Right? So we can't add this hydroxide and kick out the chloride directly, right? We need to form the tetrahedral intermediate. Likewise, when we add the methanol, we're not kicking out the chloride directly over here, but we're pushing those electrons up to the electron withdrawing group and then doing an elimination, right? So this would be the addition step, and this would be the elimination step. All right, so this all sets us up to help us better understand nucleophilic aromatic substitution. Because if you look at this, right, we have a leaving group attached to a carbon with a pi bond. Here we have a leaving group attached to a carbon with a pi bond. And a nucleophilic aromatic substitution, we're adding nucleophiles to these aromatic systems. And this aromatic system features a leaving group, which we'll just symbolize here with X. And X can represent fluorine, chlorine, bromine, or iodine. So X is just a halogen, right? So we have our leaving group X attached to a carbon that is part of a pi bond. So in nucleophilic aromatic substitution, what occurs is the nucleophile adds to that carbon with the leaving group on it, and we form an anionic intermediate. Now we have to realize that this anionic intermediate that formed from breaking aromaticity, but is still in conjugation with the other pi bonds that exist in that molecule. And so we can shift those electrons around, delocalize them throughout that ring, first putting them in the position para to the substitution. And then putting them back into the ortho position relative to the substitution. And then just like these other substitution reactions, right, it proceeds through a stepwise mechanism where the first step is going to be addition and the formation of an anionic intermediate. And then the second step will be elimination, where we kick out the leaving group to form our substitution product. Through rearomatization. So when we think about the energy diagram for this reaction, right, this reaction energy diagram is going to be very similar to others that we've seen recently, where it's a two-step mechanism. In that reaction, we're forming a high energy intermediate. We'll assume that these reactions are going to be exothermic, right? So leading to a more stable product. And it's going to be that first step that is the rate limiting step, that addition step, that is the rate limiting step. Right, and on this energy diagram, we know that because that is the highest part of that reaction pathway, right? So it's that first step, that addition step, that limits the rate. So if you think back to other aromatic substitution reactions, the electrophilic aromatic substitution, most notably, right? We learn that anything that we can do to lower the energy of that intermediate is also going to lower the energy of the pathway that we take to get to that intermediate. And in effect, if we can lower the energy of the intermediate, then we can increase the rate of that reaction. We can lower the energy barrier of that rate limiting step. So what can we do to this reaction to get it to go? So what I can say here is that if we were to take chlorobenzene and add a nucleophile to chlorobenzene, nothing would happen. That nucleophile would just stare at the chlorobenzene and they would not be able to react with each other. However, if on this molecule we add an electron withdrawing group that helps to stabilize that anion, then we can get this reaction to go. So it's important to really pay attention to this anionic intermediate and understand where that electron concentration is on that intermediate. When we add the nucleophile to the position where the leaving group exists, that's going to push the electrons over to the ortho position relative to where the substitution is happening. Right? So you can see that we're forming that anion in the ortho position, in the opposite ortho position, and also in the para position. So on that anionic intermediate, that electron density exists mostly in the two ortho positions and the para position. So if we're able to put an electron withdrawing group in those positions, that's going to significantly lower the energy of the intermediate and allow nucleophilic aromatic substitution to occur. So let's write out a rule for this. So the rule that we're going to lay down is that nucleophilic aromatic substitution will only occur with an electron withdrawing group, ortho or para, relative to the site of substitution, right? And we can say that this rule stands because the anionic intermediate must be stabilized. Right, if we can stabilize the intermediate, then we can lower the reaction rate and get that pathway to occur through a faster reaction rate. All right, so let's take a look at an example, a possible example. So we've learned that a nitro group is a really excellent electron withdrawing group. Right, and if you take a look at this, you can see that the nitro group relative to this chloride is ortho. So those two substituents have an ortho relationship, whereas the nitro group relative to this chloride, they have a meta relationship. So if we do a substitution on this carbon, when the anion forms, it will form in the ortho, or it will be concentrated in the ortho, para, and ortho positions. If we do a substitution at this carbon, now again, the anion will be concentrated in the ortho and para positions. So if we add a nucleophile, and we're going to add an amine nucleophile in pyrrolidine, and we will do this with a mineral base or a carbonate base, and we'll just use DMSO as the solvent, right? So these are the conditions of the reaction. What you really need to know is that we're adding an amine nucleophile. What we will see is that substitution will occur regioselectively at only one chloride position, right? So the substitution will only occur here because when that happens, the anion or the intermediate will be stabilized by the electron withdrawing group. If the substitution occurs here, that intermediate is not going to be stabilized by the electron withdrawing group because it is in the wrong position relative to that leaving group. So for nucleophilic aromatic substitution to occur, we need to make sure that we have an electron withdrawing group on the benzene ring that is undergoing substitution, and that electron withdrawing group has either an ortho relationship or a para relationship with the group that is being replaced, in this case a halogen group. Let's look at some of the other factors that we might have to consider. All right, and we're going to take a look at the effect of the leaving group, right? So how is that type of halogen going to influence the reaction, and also the effect of the electron withdrawing group. When we went over electrophilic aromatic substitution, we learned that there are several different electron withdrawing groups, and we'll take a look to see which of those might work better than others. Start off by taking a look at how the leaving group, the halogen that is on the benzene ring, is going to affect substitution. So we've learned last semester when we looked at aliphatic substitution that leaving group ability pretty much reflects the conjugate base stability. Right, so we can say that iodine is a better leaving group than bromine, which is a better leaving group than chlorine, which is a better leaving group than fluorine. Really the iodide, bromide, chloride, and iodide, so the anions of those atoms, right? So this is the best, and that is the worst leaving group. So if you consider a reaction where we're taking say orthofluoronitrobenzene and treating this with sodium cyanide, and we do the same reaction with iodo-nitrobenzene, again treating with sodium cyanide, we would expect that these two reactions would produce the same product, right? So we have an electron withdrawing group that has an ortho relationship to a leaving group, right? So both of these reactions are viable, and the product that we would get from both of these reactions should be the same, where the cyanide ends up replacing or substituting that leaving group. So there's no difference in the type of product that is formed between these two reactions. I think the bigger question is, how viable are these reactions, right? If we had to choose, if we had to go into the lab and choose a starting material to make this product, which of these two starting materials would we choose? Well, we understand that this reaction, again, is going through a two-step addition-elimination process. And it's the first step that is the rate-limiting step. Right, and so if we consider this to be the intermediate formed from the fluoride substitution, the question that I have is, how is this reaction pathway going to be different from the reaction pathway that we have here? Will it be the same? Would you expect the intermediate energy to be higher, or would you expect the intermediate energy to be lower? So pause the video and think about how these two reactions are going to compare in terms of rate and viability when run next to one another. Hopefully you identified that an iodide is will not be able to stabilize an anionic intermediate as well as a fluoride. Right, so even though iodine is a better leaving group, because the intermediate energy is going to be higher, then the reaction starting with the aryl iodide is going to be slower. And so when we run these reactions, even though fluoride is a poorer leaving group, because it can stabilize the anionic intermediate better, those reactions are going to be faster, right? The second step, the loss of that leaving group, is not determining the rate of the reaction, right? It's only the addition step that determines the rate of the reaction, and in reality, the energy of the intermediate. So if we're choosing an electrophile for nucleophilic aromatic substitution, although it might be seem illogical at first, right? It's actually the aryl fluorides that are the best electrophiles for nucleophilic aromatic substitution. Let's consider the effect of the electron withdrawing group, right? And realize that we've looked at in the past couple of chapters several different electron withdrawing groups. Maybe before we go over this, you can write some of those electron withdrawing groups out just to remind yourself of what an electron withdrawing group is. All right? Ultimately, electron withdrawing groups are going to affect the energy of the intermediate and therefore the rate of the reaction. Right, so some electron withdrawing groups are going to be stronger than others and will more easily hide that charge that forms or delocalize that charge that forms. Right, so let's take a look at the relative rates of some different electron withdrawing groups. All right, and we're going to use the term KREL, which is just relative rate constant. And we're going to say that a nitro group it has a KREL of 1, right? And so this is just going to be our standard group, right? We're just saying if the nitro group is 1, what are other electron withdrawing groups, what are the rate constants of other electron withdrawing groups relative to that nitro group? Well, hopefully one of the electron withdrawing groups that you just drew out is a sulfonyl group. All right, and so we're going to just show this being R. R can be alkyl. It could also be heteroaromatic, so we learned how to make sulfonic acids whenever we went over electrophilic aromatic substitution. Well, in this case, the relative rate constant for a sulfonyl group is going to be 0.056. Right, so we're saying that if we have a benzene ring with a nitro group on it, and we're comparing that to a benzene ring with a sulfonyl group on it, the nitro group will be approximately 18 to 20 times faster, the reaction, the addition of a nucleophile to this electrophile will be 18 to 20 times faster than having this electron withdrawing group. All right, another one that we can look at, a common electron withdrawing group, is a cyano group. In this case, the relative rate constant is going to be 0.031. Right, so a nitro withdrawing group is approximately 30 to 35 times more effective as an electron withdrawing group. And then finally, very common electron withdrawing group, right? And one that we looked at when we investigated conjugate addition is the carbonyl electron withdrawing group. Carbonyls are effective electron withdrawing groups, not quite as effective as the others. And so these reactions would occur approximately about 80 times slower than a benzene ring with a nitro group on it. All right, so let's take a look at a couple of just really simple examples. For each of these reactions, we're going to use a fluoroarene because we know that fluoride allows us to accomplish the best nucleophilic aromatic substitution reactions. Right, and then if we treat this with sodium methoxide and methanol, and then maybe heat it up a little bit, we'll get substitution at the fluoride to make an aryl ether. Right, and we can do the same thing if we have a ketone. Right, so orthofluoroacetophenone. Again, if we take sodium methoxide and methanol, heat it up to the same temperature as the reaction above, again, we'll be able to accomplish that substitution and make the same product. Oh, sorry, that should be a ketone. All right, so when we look at these two reactions, what we learn from this data up here is that the reaction that occurs, or the substitution that occurs with the orthonitro substituent, that's going to be approximately 80 times faster reaction rate. Whereas if we put this ketone on, replace the nitro group with the acetyl group with the ketone, right, that's going to be approximately 80 times slower reaction rate. So the type of electron withdrawing group does matter. We're not going to parse those out too much, right? We're not going to say that you can't accomplish a nucleophilic aromatic substitution if you have a poorer electron withdrawing group. And actually, these are not the only electron withdrawing groups that you can have. But it's good to understand that not all electron withdrawing groups are going to have the same stabilization capability of that anionic intermediate. In the next video, we're going to just take a look at a couple of specific examples of nucleophilic aromatic substitution. But at this point, you should know, or you should be familiar with the basics laid out in these two slides.